Good morning, everybody. Afternoon, I should say at least. My apologies for the slight late start due to load shedding. I've been forced to start later because there is no additional power supply or generator in this section of the building. So, my apologies on behalf of the physics team. Okay, but first, before I continue, I just want to fix some stuff here. But today we'll be doing universal gravitation and oscillatory motion. Okay, I just want to fix the camera here. I think it's the other way around. Okay, usually I do this beforehand, but as I said, there was load shedding, so I couldn't. Okay, let me just move this a little bit out of the way. Okay, there we have. After all, you did not come to see me, you came to watch some interesting physics. Now I need to just expand one more page and then we'll be ready to go. Okay, there we go. Let me just see how it looks. Okay, so universal gravitation. This is on section 15.1. 15.1. Okay, I want to see if you can see what I see. There's that lag again. Just trying to fix that too. Universal gravitation. This is our topic for today, with some oscillatory motion in. A beautiful, beautiful section of physics. Universal gravitation. A law developed by the English physicist Sir Isaac Newton. Okay, there are 2 viewers at the moment. Okay, would you guys like me to set up a Teams meeting? Okay, let me just see. I join it now. If you wish to join me on Teams, please feel free to do so. And let's get into it. Okay, universal gravitation. Okay, I've been trying to fix the lighting in here. Let me just see. Oh, if that's better. Looks a bit better, but not optimal. But yes, okay. If you have any questions or any problems, please ask me in the chat. Okay, or I just turned on my Teams meeting. You can just join the Teams meeting. I see there are no one in the Teams meeting yet. So if you would like to speak to me through Teams, please feel free to do so. Otherwise, you can just follow what I do here, but please give me an indication that you want to talk on Teams, because I'm going to have to flip between the multiple screens I have open, the tabs I have open. Okay, universal law of gravitation, like I said earlier, was developed by Sir Isaac Newton, the English physicist, the man who started all of this. Now, Newton's law of universal gravitation, okay, our entire governs the motion of planets and our entire universe. Okay, it has been superseded by Einstein's theory of gravitation, also more commonly known as Einstein's general theory of relativity, which encompasses gravity, but it is a theory of gravitation nonetheless. Okay. Doesn't mean Newton was wrong, it just means Einstein is a bit better. Now, Newton's law of gravitation. Now, Einstein's theory of general relativity is way beyond the scope of this course or even my abilities, so I will leave it at that. This is Newton's law of universal gravitation, okay, named after Isaac Newton. Okay. People are always mistakenly told that Newton discovered gravity while sitting under an apple tree and an apple fell on his head. That is not the truth. Newton himself said that he was occasioned by the fall of an apple while sitting under an apple tree. Okay, meaning he just witnessed an apple fall and started thinking about, which started a train of thought, which eventually led to the universal theory of gravitation. Now, Newton's law of gravitation says the following: the gravitational force of attraction. Now, gravity can only be attractive. Okay, Newton's law of gravitation says the gravitational force of attraction. This is what the law says: the gravitational force of attraction so the gravitational force of attraction between any two particles with mass m1 and m2 separated by a distance r has the magnitude F g for gravitation is equal to the gravitational constant g multiplied by the mass of one particle multiplied by the mass of the other particle divided by the square of the distance between the two particles. Okay, that is how you calculate the force of attraction between two masses. Okay, that is how you calculate the force of attraction between two masses. Now, the between any two masses. Let me see if there is in the Teams meeting anyone. No one has joined. But let me continue. The free fall acceleration. Okay, this is important. You will use this equation most predominantly when dealing with universal gravitation. There is also another one that you might have to use from time to time. This one deals with the free fall acceleration, which was sometimes asked to calculate. Okay, now the free fall acceleration g, which we know to be 9,8 near the surface of the earth, is not always constant. It changes with height. Okay, now it changes according to the following relation. Okay, it says the free fall acceleration g the free fall acceleration g, it's some height h, or the free fall acceleration g at some height h, which is above the earth's surface, some height h above the earth's surface, sorry, above the earth's surface is equal to the following, or can be calculated as follows. Okay, so this is how you calculate the free fall acceleration g above the earth's surface is equal to the gravitational constant multiplied by the mass of the earth divided by r squared, which is equal to the gravitational acceleration multiplied by the mass of the earth divided by the radius of the earth plus the height above the earth squared. That whole sum squared. So this formula here is how you would go about calculating the free fall acceleration above the earth. Now, as you can see, since the radius of the earth is very large, this h here will have a very small effect. Okay, so it's going to be negligible for distances such as 5 to 10 meters. Okay, it's not going to have an impact on the overall gravitational acceleration. Okay, but just keep in mind that it does change, even though it's very slight, it does change due to your height above the earth. So your gravitational free fall acceleration, or just your gravitational acceleration, does change due to your height above the earth. Okay, so there are no questions yet. Let me see, none at all. Still no one has joined the Teams meeting yet. No one on YouTube chat yet. So those that are currently viewing, if you have questions, please ask me. Okay, so we are dealing with the universal law of gravitation, and currently we have dealt with two formulas that we will be using mostly when dealing with universal law of gravitation. The first one is this force relation, which tells you that the force between two masses m1 and m2 is directly or proportional or to the product of those masses and inversely proportional to the distance between those two masses squared. Okay, so basically it says the force between any two particles m1 and m2 is equal to the gravitational constant multiplied by the product of their two masses divided by the distance squared between the two particles. Okay, so also the gravitational acceleration g is equal to the gravitational constant multiplied by the mass of the earth divided by the radius of the earth plus the height above sea level. And that whole height, that whole sum of those two heights squared. Okay. Now let's get into a problem Okay, three uniform spheres of mass m1, m2, and m3. Okay, I don't going to write it down. I'm going to rather give you the drawing. Okay, so I'm going to give you the drawing. There are no problems here on this universal acceleration, so I will be giving you the problems via a drawing. Okay, but the problem is three uniform spheres of masses m1, m2, and m3 are placed at the corners of a right triangle as shown in the figure. Okay, calculate the gravitational force on the object of mass m2. Okay, so I'm going to draw the system and then we're going to work from there. So here we have a mass, here we have another mass, and then here we would have another mass. Okay, so the forces, all of these masses, since they have mass, exhibit a force on each other. Okay, so this mass has a mass of 6 kilograms. Okay, this one 4 kilograms. Okay, the units of these masses are in kilograms, and this one 2 kilograms. Okay. The distance between these two is 0.3 meters. Okay, so the distance between the two of them is 0.3 meters. And we have here the distance between these two is 0.4 meters. That is 0.3 meters, and this one is 4 meters. Sorry, not 0.4 meters, it is just 4 meters. Okay, now we have a mass of 6 kilogram, a mass of 4 kilogram, and a mass of 2 kilogram, and we are asked to find the following. The question is three uniform spheres, which is what we just drew here. These are the uniform spheres, have masses 2 kilogram, 4 kilogram, and 6 kilogram. Okay, we drew that. They are placed at the corners of a right triangle as follows, and I have drawn you how they are placed. Okay, calculate the gravitational force on the object of mass m2. Okay, so we need to calculate the gravitational force on the 4 kilogram mass. So the gravitational force, calculate the gravitational force. These are my own notes, by the way. Force on the 4 kilogram mass. Okay, so we need to calculate the gravitational force on the 4 kilogram mass. Okay, assuming that the spheres are isolated from the rest of the universe, meaning there are no other gravitational forces acting on these spheres, only these spheres. Okay, now let's call these spheres sphere number 1. Let's call this one sphere number 2, and we'll call this one sphere number 3. Now all of these spheres have an effect on each other because they all have masses, and according to Newton's law, any two points that have a mass must have a gravitational force between them, and we are asked to calculate the gravitational force on this 4 kilogram mass, or m2, which is equal to the 4 kilogram mass. We are asked to calculate the force on m2. Now the force on m2 can be as follows. Okay, the 6 kilogram force will be pulling M2 towards the right in the direction which I drew here, and thus 2 kilogram mass will be pulling M2 upwards, while the 6 kilogram will be pulling it to the left. Okay, so we can call this force here the force that 3 has on 2. Okay, and this one you can now call the force that 1 has on 2. Okay, that is that force. Okay, so first let's calculate the force that 1 has on 2. The force that 1 has on 2. Okay, so the force, that is the bar for force that 1 has on 2. That force. Okay, so it is equal to, move this up a bit, the force that 1 has on 2, meaning the force between sphere 1 and sphere 2. Okay, we are asked to calculate the net force on sphere 2. So the force that sphere 1 has on 2 is equal to G multiplied by the mass of 1 multiplied by the mass of 2 divided by the distance between them squared. Okay, now what is G? It's the gravitational constant. It is equal to 6,67 times 10 to the 11, and it has units down here, but normally it has units of Newton meters per kilogram squared. Okay, it has Newton meters per kilogram squared, but I'm not going to put them in here now because I don't think I'm going to have enough space. Okay, so the mass of one of the spheres of sphere 1 is equal to 2 kilograms. I do not put in units while actually putting it in, but it is a good habit to do that. Divided by the distance between them, which is 0.3, and remember that distance must be squared and in meters. Okay, that gives us a force between 1 and 2 to be equal to 5. By the way, this is in the I hat. This is in the J hat direction. Sorry, the J hat direction. Okay, so we don't have to say upwards or anything. So we can just say in the J hat direction. This is 5.93 times 10 to the negative 11 in the positive J hat direction still. Okay, it's still in the positive J hat direction, and the unit is newtons. Okay. So there we have the force between 1 and 2. Now the force between 3 and 2. Okay. The force that 3 exerts on 2. Okay. We calculate it the same way, the gravitational constant multiplied by the mass of 3 times the mass of 2 over the distance between them squared. The gravitational constant, 6,67 times 10 to the negative 11, multiplied by the mass of 3, which is 6 kilograms, multiplied by the mass of 2, which is 4 kilograms, divided by the distance between them, divided by the distance between these two spheres, which is 4 meters, and we need to square that. That gives us the answer of, if I calculate it correctly, 2.97 times 10 to the negative 9 newtons, or no, sorry, that is the wrong one. I wrote the wrong answer. I have so many problems here. This is in the negative J hat direction. This will be pulling it in the negative I hat direction. That is in the positive J hat direction, and it is in the negative I hat direction. So the answer will be negative 10,0 times 10 to the negative 11 in the I hat direction. Okay, so it is in the I hat direction, but just negative I hat. Okay, because this sphere number 3 push behaving. Since gravity is always attractive, it's pulling it towards the left, which is in the negative I direction. Okay, if you have any questions regarding that, please let me know. But I'm going to continue. That was just a warm-up problem, so that you guys can get familiar with using Newton's law. Okay, now the question did ask what was the force on the M2. Okay, but we're not going to calculate the net force. We are just calculating the force between 2 and 1 and the force between 3 and 2. Okay, the reason for that is I want you to get familiar with this formula. Okay, now I'm going to give quite one or two more problems on using this universal law, like two more, and then we are done with the introduction to this law. We will move on to what you guys did in PHYV in the tutorial. We will go through those answers. Okay, so for now, this is just to familiarize yourself with the universal law of gravitation. So I'm going to give you another problem. It's a very simple problem. It is just so that you can familiarize yourself with Newton's law and how to use it. So let's see. This is two spheres, isolated of course. One has a mass of 2 kilograms, the other also has a mass of 2 kilograms. And these two spheres are separated by a distance of 30 centimeters. Okay, so 30 centimeters separates these two spheres. And we call this one M1, we will call this one M2. So that is the problem. Obviously, the question then naturally becomes, calculate the force between these two spheres. So F is what we need to calculate. Okay, so how do we go about calculating the force? F is equal to G times M1 times M2 over R squared, which is the distance between them squared. Now G, we know, is 6.67 times 10 to the negative 11 times the product of their masses, which is 2 kilogram times 2 kilogram over the distance squared. Now we always work in meters, so it's 0.3 meters squared. And that gives us an answer, the one I mistakenly wrote down earlier on. Gives us an answer. If you go on your calculator, it will give you the answer of 2.97 times 10 to the negative 9 newtons, or 2.97 nanonewtons. Okay, that is the force between these two spheres that I drew there. You see, it's almost a negligible force. It's a nanonewton. Okay, 1 billionth of a newton. So the force is very small between two kilogram forces. Now imagine two atoms or two electrons, which has a mass that is very small. The atom is 10 to the negative 27, 10 to the 27, negative 27, and the electron is 10 to the negative 31. I could be mistaken, but yes, that is what I remember. I think I can remember from quantum mechanics. But anyway, so that is the force between 2 kilogram spheres separated by a distance of 30 centimeters. So a ruler's length from each other. Just a side note, if we look at this formula, you will see that gravitational forces will increase as the masses get bigger, because gravitational force is directly proportional to the product of the masses and inversely proportional to the distance between their two centers, meaning that if the distance between the two particles become larger, the force between them becomes smaller. And I think you guys might have known by now that there are 4 fundamental forces: the gravitational force, the electromagnetic force, the weak and the strong nuclear forces. And of all of those, gravity is the weakest. But x over the largest distance though. Now, let's see. Two objects attract each other with a gravitational force of magnitude 1 times 10 to the negative 8 when separated by 20 centimeters. If the total mass of the two objects is 5 kilograms, what is the mass of each? Okay. Let's say we have two objects, okay? We have two objects, M1 and we have M2. Okay. The force of gravity between M1 and M2, the force that one has on 2, is equal to 1 times 10 to the negative 8 newtons. And they are separated by a distance of 20 centimeters, meaning 0.2 meters. So we have M1 and M2, and we're given that the force between M1 and M2 is equal to 1 times 10 to the negative 8 newtons. Okay. Continuing, we are also given that the total mass, okay, the mass mt of the two particles is equal to M1 plus M2 is equal to 5 kilograms. They want to know what is M1 and what is M2 given the information provided. So we are provided that M1 and M2 are separated by a distance of 0.2 meters and the force between them is 1 times 10 to the negative 8 newtons, and that the total mass of M1 plus M2 is equal to 5 kilograms. Given that information, they want us to work out the mass of each of these two particles. Okay? Let's continue. So, we know that the force between them is calculated as follows. F is equal to the gravitational constant multiplied by M1 multiplied by M2 divided by R squared between them. Okay. Now the force is given to us to be 1 times 10 to the negative 8 newtons. The gravitational constant is equal to 6.67 times 10 to the negative 11. Then we have the mass of one particle, M1, multiplied by the mass of M2. But M2 plus M1 should equal 5 kilograms, which means that M2 is equal to 5 kilograms subtracted by M1. Okay. So M1 times M2, but we know that in this case M1 plus M2 is equal to 5 kilograms, meaning that M2 is equal to 5 kilograms minus M1. Okay, so that is just M1 multiplied by M2 over the distance between them, which in this case is 0.2 meters squared. And that will give you a force of 1 times 10 to the negative 8, supposedly. Okay. Now, going on. If we solve for M1, then automatically we get M2 because we just subtract M1 from M2. Okay. Rearranging this equation, we get M1 and M2 alone. M1 alone, we get that 5. On this side, we get 5 kilogram, 5 kilogram multiplied by M1. If we multiply it in, minus M1 times M1, we multiply it in. This is just 5 kilogram multiplied by M1, multiply M1 by M1, we just get M1 squared over 0.04 m squared. And on this side, we still have 6.67 times 10 to the negative 11 newtons, Newton meters per kilogram squared. Okay. So I've simplified this section and wrote it first, and this is just what was there first, and this was equal to 1 times 10 to the negative 8 newtons. Okay. If we continue, and if we take that over, we must multiply on that side and then divide by 6.67. We are left on this side with the following: 5.0 kilogram multiplied by m1 minus m1 squared. That is what we're left on the right hand side, and on the left hand side we now have the force 1 times 10 to the negative 8 newtons multiplied by 0.04. Basically this is high school math. We're just clearing all the clutter from that side, divided by 6.67 times 10 to the negative 11. Okay, rearranging it further, taking this over to that side and then calculating this, we get 6 kilograms squared. This gives us 5 kilogram times m1 minus m1 squared. Okay, now continuing, we get the following. If we put them all on one side, if we move that to this side, we get m1 squared minus 5 kilogram m1 plus 6 kilogram squared equal to 0. This is a very simple quadratic equation which you solve. Either you can use the formula, or you know from high school the two factors that will give you 5 is 3 and 2, and this will be m1. The symbol in front of the last one is a positive, so both of them will have the sign of the middle term, so both minuses. So m1 will be equal to 2, therefore m1 is equal to 2, and m1 will be equal to 3. m1 is equal to 2 kg, or m1 is equal to 3 kilograms. Okay, that will make the other one then obviously equal to 2 and 3 if you subtract them from 5. Okay, giving that m2, if you have m1, you can then just use this formula that m2 is equal to 5 minus m1. We've established that m1 can be either 2 or 3. Okay, so continuing, that is the final problem we have to sink our teeth into. Now we can continue to the problems on what we did for the tutorial session. Okay, we can continue there. It is quite involved. Some of those problems take quite laborious and time consuming, but I'm going to have to go drink water first because my throat is getting a bit dry, and I think I want to use. Okay, that's nice. Yeah, okay. I have an hour left in the session, so I will go drink some water. It's halfway through. And again, my apologies that we started a bit late due to load shedding. But we are well on course and we will be able to finish in time, I believe. Okay, so I'm going to put up the problem that we are going to start doing now, or the problems that we'll start doing now. I put up the first one. Okay. I'm going to put them up now. Now, there's some practice quiz. We are at this one, oscillatory motion. Continue the mouse speed. We are currently at problem number. By the way, this is the problem that we did in the beginning. Okay, I realized that after I done it, I said, ah, what the hell? Problems is problems. Okay, can never have too many those problems. Okay, so we start at question number 8. The figure below shows a sine wave at one point of a string as a function of time. Okay, so this is a fast sine wave as a function of time. Okay, now the question asks, use the observable. Let me see if I can switch this light on. It's getting a bit dark here. It's a ring light, and it doesn't work very well for me in the past. Let's see. So due to the fact that it casts such shadows that I do not like, or that I'm opposed to using it because the shadow effects it creates. Ideally, I would love to place it here, but there are so many. Aha, I think I found a perfect spot. Okay, well, relatively perfect. Okay, so I will be back in a minute. Just gonna go drink some water. Okay, let's get back to it. See, no one has said anything yet. Okay. First question. Did you bring it out? Okay. Question number 8. Okay. The figure below shows a sine wave at one point of a string as a function of time. Okay, so that is a sine wave. Okay. Before we go into this question, let me just describe a wave for you. Okay, so this would be a typical wave, typical sine wave. Okay. The height from a crest to the equilibrium, that height there is its amplitude. Okay, the highest, the maximum height from the crest to the equilibrium is the amplitude. The distance to complete one full wave is its wavelength. Okay? That is its wavelength for one complete wave. the distance between any 2 points in phase, these 2 points are in phase, is its wavelength. Okay, and this is time, by the way, and that is height, y. So that is basically what you need to know for this next question. Okay, it says use the exhibit to answer the following questions if given that particular sine wave. There it says refer to exhibit 16.1. Okay, which of the graphs below, it's raining nicely outside, which of the graphs below shows a wave where the amplitude and frequency are each reduced in half? Okay, now if the amplitude is halved, then this wave will look something like this. Okay, if the amplitude is half, let's say that is 2, then its amplitude will be 1 somewhere here, so it'll be closer to the equilibrium. So let us redraw this wave. So that is 2 where it originally was, okay, and that is 1. So this wave will now look like this. The same wave that we drew on top, sorry, it'll now look like that. Sorry, this bottom part should be just a bit smaller, but yeah, this is now 1. Its amplitude is now 1, so it'll have a smaller amplitude. So the wave will look much closer. The highest point, or the crest, will be much closer to the equilibrium. And they say the frequency is reduced to half. Okay, now if the frequency, we know that speed is equal to wavelength times frequency, which means that frequency is equal to speed over wavelength. Okay, meaning that frequency is inversely proportional to wavelength. So if the frequency is half, if the frequency is halved, that means this wave, this particular original wave that I drew here, wave number 1, is our original wave. So this is when we halve the amplitude. We halve amplitude. This wave is what I drew when we halve the amplitude of this wave. Now let's halve the frequency. When we halve the frequency, if we halve this, it means that this must double, the wavelength must double. Okay, so if we halve, this is the first, this is the original, then we halved the amplitude, now we are halving, this is time, we halve the amplitude, now we are halving the frequency, meaning the wavelength doubles, meaning this is what we will get now for this particular wave of ours. Okay, and it will start going that way again. Okay, so if we halve the frequency, the wavelength doubles, meaning only half of this graph, half of this sine wave will be to that point. Okay, meaning that in this particular graph it's going to become closer to the equilibrium, but only up to this point here. I don't know if you can see my cursor, only up to this point will be in the graph because of the halved frequency, meaning the wavelength is getting longer. So only up to the crest here, the trough will be only up to the trough. The minimal point here will be in the actual graph that we want. So let's see, it can't be that one because the frequency still looks the same. It is the exact same graph. Okay, it can't be this one. The frequency is increased here. Another frequency, the amplitude is increased, it's bigger, it should be smaller. Okay, this one's amplitude is smaller, but it's still the same wave. Its wavelength did not double. This one, its amplitude, its wavelength has doubled, but its amplitude is still the same. This one's amplitude is halved and its wavelength has doubled, which means this is the wave we want. Number E is the correct one. Okay, so answer for 8. So answer for 8 is E. Okay, because the wavelength has doubled and the frequency. has the wavelength is halved and the frequency is halved, which means the wavelength is doubled. Okay. Now the next one involves the use of Kepler's laws. Okay. Newton set up his universal law of gravitation and based it on the laws discovered by Johannes Kepler. With the help of the laws discovered by Johannes Kepler. His science built on the work of others. Okay. Now, this problem says, problem number 9. Now, there are various of Newton's Kepler's laws. We will only be using one. Okay. The amplitude law. I wonder if I should write the law down in its pure form, but let me just ignore that for now. Kepler's law. I'm going to show you Kepler's law. I have the answer for it, but I'll write it in its pure form. It has to do with the perihelion. Now that is its second, the first, the second, I'm looking for, yep, there it is. Third law. Kepler's third law. Now Kepler's third law, we will write it down. Okay. Kepler's third law states the following. It states that the square root of the period, you can just listen, I'm going to write it down. It says, I'm going to write it in formula form. Okay. Kepler's third law states that the square of the period is proportional, the square of the period is proportional to the cube of the semi-major axis of the orbit. Okay. So the square of the period is equal to 4 pi squared over the gravitational constant times the mass times the distance r, or the radius cubed. Okay, that is Kepler's third law. Okay, let me see if I can't. I am just having problems with lighting today. Okay, this is a massive problem today. Okay, so that is Kepler's third law. Now we are just going to use Kepler's third law in its various forms. So, you're just going to use Kepler's law, but in a different form. You're just going to make the time, where t is the time or the period that it takes to complete one orbit. 4 pi squared, that is a constant. 4 pi is a constant. That is the radius of its orbit. That is the gravitational constant, and that is the mass of the particle. In this case, I will call it the particle around which this thing is orbiting. Okay. So it says, the question is, a 50 kilogram satellite circles this mass of the orbiting mass. The mass around which this satellite will orbit. It says a 50 kilogram satellite circles planet Pluton every 5.6 hours in an orbit with a radius of 12 times 10 to the 6 meters. What is the magnitude of the gravitational force on the satellite by planet Crouton? Okay, so the magnitude of the gravitational force on the satellite by planet Crouton. First, we need to find the mass of planet Crouton. Okay, now we can use this formula to determine the mass of planet Crouton. Okay, because it says that the period squared which it takes for the satellite to orbit planet Crouton is equal to 4 times pi squared times the radius of its orbit, the satellite's orbit cubed, divided by the gravitational constant divided times the mass of planet Crouton. Okay, now we are given that this period of oscillation, if we arrange this to get this mass, we want that, the mass, because we want the gravitational force between planet Crouton and the satellite. Now if we rearrange this formula, Kepler's third law, we get that the mass of planet Crouton would be 4 pi squared times the radius of the orbit of the satellite cubed divided by the gravitational constant times the period squared. Okay, now if we fill in or substitute all that we know, 4 pi squared times the radius of orbit, which is in this case 12 times 10 to the 6 meters cubed, don't square that, times 6.67 times 10 to the negative 11 Newton meters kilograms squared, I believe, over the period. In this case it is 6 hours, but we only work in seconds, so 5.6 hours, so it's 5.6 times 60 minutes times 60 seconds. Okay, if we work that out, we get the mass of planet Crouton to be 2.516, at least that is what I got, times 10 to the 24 kilograms. So this is the mass of planet Crouton. Okay, that is the mass of planet Crouton. Now that was not the question. The question was not what is the mass of planet Crouton. The question was calculate the force of gravitation between the satellite and planet Crouton. Okay, now we've already done that because that mass is equal to, well, we have calculated it. We found the mass of planet Crouton because we needed it. We need it to calculate the force between planet Crouton and the satellite. Okay, so the force of gravity between planet Crouton and the satellite is equal to G times the mass of planet Crouton times the mass of the satellite, MC and MS, the radius between these two, or the distance between them, in a radial direction. So the gravitational constant is 6.67 times 10 to the negative 11 multiplied by the mass of planet Crouton, 2.516 times 10 to the 24 times the mass of the satellite, which is 50 kilograms. The distance between them is still just 12 times 10 to the 6 meters, and that should be squared. So the force of gravity between these two planetary bodies, in this case I'm calling the satellite a planetary body, not a planetary body, just a space body. Let's call it a space body. The satellite and the planetary body of Crouton. Okay, so 6.67 times 10 to the negative 11 multiplied by 2.516 times 10 to the 24 times the mass of the satellite divided by the distance between them should give us a force. If you work it out, you will get a force of 58,269 Newton between these two bodies. And if we go to where it is, do we have an option for 58? There we have it, there, 58 newtons. We check, are we correct? We are correct, 58 newtons. Okay, at least we got 58.2, but yeah, they will accept 58 newtons. Okay. Continuing, question number 10. Question is, a satellite is in a circular orbit about the Earth at an altitude at which air resistance is negligible. Which of the following statements is true? Okay. There is only one force acting on the satellite. There is no air resistance. Okay. The satellite is not touching anything. There is no air resistance. So there is only one force acting on the satellite, and that force should be gravity. Okay. There is only one force acting on the satellite. That is correct. There are two forces. There cannot be two forces. Not there are two forces acting on the satellite, and the result is no. There is only one force acting on that body. And question number 10, it is correct. Question number 10, the answer is A. Okay, A is the answer. There's only one force acting on that body. Question 11. Another problem that would involve Kepler's third law. Okay. Number 12, number 13, and then number 14 and 15. Okay, I'm going to do number 11, then I'm going to go 14 and 15, then I'm going to come back to number 12. Okay, number 12 and 13. Number 11, in this case, a satellite circles planet Roton every 2.8 hours in an orbit having a radius of 1.2 times 10 to the 7 meters. Okay. If the radius of Roton is 5 times 10 to the 6 meters, what is the magnitude of free fall acceleration on the surface of Roton? Okay. So first we need the mass of Roton. Okay. So we can work that out using Kepler's law, because we're going to need the mass of Roton if we want to find the free fall acceleration on planet Roton, on the surface of planet Roton. Okay. So we have used this formula before. The mass of planet Roton would then be equal to 4 times pi squared times the radius of the orbit squared cubed divided by gravitational constant times t squared. Okay, by the way, I did not put the square. Did I put the square in here? Previous problem, I did square it in the answer. I did square, but I'm just wondering if I actually put it the symbol form. Okay, here I did not put it in, but there should be a square there. Okay, I didn't put it in. I forgot to put it in, but the answer will not change in my calculations. It stays the same. But here, okay, let me try to put it in now. So if we substitute all that we've been given, that's 4 pi squared. The radius of this orbit is 1.2 times 10 to the 7 meters cubed over 6.67 times 10 to the negative 11 Newton meter. I think there is one here. We just make sure that the units of Newton meters per kilogram squared. So I was right the first time. The t period that is squared, the period squared, in this case the period is 2.8 hours, but we only work in seconds, so it's 2.8 hours multiplied by 60 minutes multiplied by 60 seconds gives you the number of seconds in 2.8 hours, and that will eventually give you a mass of planet Crouton which is equal to 1.1 times 10 to the 20 roton, in this case to 25 kilogram. That is the mass. 10 to the 25 kilogram is the mass of planet Roton. Okay. Now we have gotten a formula for free fall acceleration at the beginning of this lesson. Okay, it is equal to the gravitational constant multiplied by the mass of the planet, in this case planet Roton, divided by the radius of the planet, in this case planet Roton, plus the height above the planet. In this case, it's at the surface, so h will be 0. Okay? The radius of planet Roton is 5 times 10 to the 6 meters. Sorry, it should not be there. Plus the height above the surface. It's at the surface, so the height h is 0 squared. That is 6.67 times 10 to the negative 11 multiplied by the mass of planet Roton, which is 1,1. 10 to the 25 kilos. Not putting in the units. So the free fall acceleration will be 26.84 meters per second squared. Which is, that by the way is in 60 minutes in an hour. And that is 60 seconds in a minute. That is 26.4 seconds. We round it up, it becomes 27 meters per second square. Okay. So there we have the free fall acceleration on planet Roton. Okay, we use the formula for free fall acceleration, which says that free fall acceleration at some distance above the surface of the planet is equal to the gravitational acceleration, the gravitational constant multiplied by the mass of the planet, which in this case is planet Roton, hence the subscript r, divided by the radius of the planet, which is planet Roton, plus the height above the planet, which is at the surface, so h will be 0. If we substitute everything in, we have the mass of planet Roton, we have the gravitational constant, we have the radius of planet Roton, and it is at the surface, so it's 0, and we get 27 meters per second. Okay. So let's just put something. Earlier on, I told you the mass. The mass of the Earth. In this case, on this planet Roton, you would accelerate towards the Earth at 27 meters per second. So your weight would be much higher on planet Roton than on Earth. If that is the case, then that means that planet Roton must either have a smaller radius than the Earth, or it must be much more massive in terms of matter than the Earth. Let's check the mass of the Earth. The mass of the Earth is 5.9 times 10 to the 24, and planet Roton is times 10 to the 25. So planet Roton is indeed much more massive than the Earth. Okay, number 12, 27, what's the answer? Let's check. Number 12 and number 13 I will come back to. I want to go to number 14 and 15 and do them quickly. This is number 10, this is number 11. Number 12. Oh, I wonder if I should just do them now, because I'm going to have to do them eventually. So let me just get to it then. Let me just do it. Number 12. 3 5 kilogram masses are located at points in the xy plane as shown in the figure. Okay. So we have 3 5 kilogram masses as shown in that figure, and they are located at those points. Use this exhibit to answer the following questions. What is the magnitude of the resultant force caused by the other two masses on the mass at x equals 0.4 meters and y equals 0? So they want the force, the net force, the resultant force on this mass here. Okay, the mass here on your right hand side, the mass on the right hand side. The mass on the x-axis on the right hand side. Okay, so where x is equal to 0.4 meters and y 0, so the mass on the x-axis but at the distance of 0.4 from the origin. This mass here is at the origin. This mass is not at the origin. So they want the net force on this mass. Okay. Now these two masses. This is the mass that we want. This is a mass of interest. Okay. Yes, 5 kilograms. Wait. There's a mass of 5 kilograms. Now the force, the mass at the origin will pull it towards the left, while the mass on the y-axis at y.3 and x0 will pull it in that direction. Okay, that is the force on these masses. Okay, now let's first work out these two forces. Let's call this force 1 and that one force 2. Let's work out force 1 and force 2. Okay, now there are three 5 kilogram masses. So, but the distances between them are not the same. The distance between these two masses are 0.4 meters, while the distance between those two are 0.5, if you remember your Pythagorean theorem. Okay, so the force F1 is equal to G M1, we call it M1 and M2, and R squared. G is equal to 6.67 times 10 to the negative 11 multiplied by the mass. One is 5 kilogram times the mass of the other is 5 kilogram, and the distance between them for the force of F1 is equal to 0.4 meters, and it should be squared. That gives us a force equal to 1,04 times 10 to the negative 8 newtons. Okay. F2, on the other hand, is a distance. The distance between those can also be calculated as G M1 M2 over R squared. Now G in this case is 6.67 times 10 to the negative 11 multiplied by, hold on to your heads, 5 kilogram and 5 kilogram divided by the distance between those two. In this case, I'm talking about the distance between these two now, and according to Pythagoras, the distance is 0.5 meters, and it should be squared, giving us a force between those two is equal to 6.67 times 10 to the negative 9 newtons. They want the magnitude of the resultant force. Okay, so now you have two forces, one to the left and one to that side. Okay, now you can, of course, now draw a triangle. Let's with these forces find the net force. Now you have this situation. You have, this is that mass that which we are you have this force here and you have this force here, horizontal force. Okay. And you have that one there. That distance there that distance is equal to 0.4 meters, and that distance is 0.5. That distance is 0.3. Okay. It is a right angle triangle. Okay. Now that is force number 2, and that is force number 1. Let me redraw the triangle. Okay, so there's more realistic. The distance is, that is F whatever, that is F2, sorry, that is F1, and that distance there, this distance is 0.5. Well, this distance here is 0.4, this distance here is 0.3. Okay, so now we have those three distances. Okay, we can work out the angle there, theta, using the distance if we have F1 and F2, and also we have 0.3 and 0.4 as the distances. So let's work out theta. Okay. Theta is equal to the sine, is equal to the inverse tangent, and this is basic trigonometry of 0.3 over 0.4, opposite over adjacent, 0.3 over 0.4, and that gives you a theta value of 36.87 degrees. Okay. Now let's calculate the components of F2. Okay, F1 only has a horizontal component, so F1 only has a horizontal component. F1, the horizontal component, or we can just call it the X component, is equal to just the force of F1, which in this case is 1,04 times 10 to the negative 8 newtons. Okay, so that is the horizontal component of F1. F2, on the other hand, has both a horizontal and a vertical component. So the horizontal component for F2, X component, is equal to, it has an X component, which you can calculate to be the cos of 36 36.87 degrees, is equal to that horizontal component, the X component, over the F2, which in this case was 6.67 times 10 negative 9 newtons. Therefore, the X component is equal to 5.36 times 10 to the negative 9 Newton towards the left. Okay, so now we have an X component and we also have a Y component. The Y component will be exactly the same, except for this case it will just be the sine of 36. In this case I'm going much faster because we're just breaking them up into components, something you can do in your sleep by now because you have done breaking vectors into components during the entirety of your first term. Okay, therefore, that's why I'm not spending a lot of time on it, because you can do it by now. It is equal to 4 times 10 to the negative 9 newtons. So now we have F1 is into its components and F2 is into its components. Now if we sum them up, the net x component and the net y component, we will find that the net y component, okay, so the x component and the net y component and it is attractive in this direction and in upwards. So the net x component, the net x component equal to this x component plus that one gives you 1,04 times 10 to the negative 8 plus newtons plus 5.36 times 10 to the negative 9 newtons, and it equals 1.57 times 10 to the negative 1.576 times 10 to the negative 8 newtons. That is the force in the x direction. Now the net y component is equal to just the y component to work out, which is 4,0 times 10 to the negative 9. So now newtons. So now we have an x component and a y component. Okay, and we can then just work out using Pythagoras the net force. So F resultant is then equal to the square root of the sum of those two squared. And so 1.57 times 10 to the negative 8 squared plus 40 times 10 to the negative 9 squared, and the square root of that gives us a resultant force of, if you work it out, you should get 1.63 times 10 to the negative 8 Newton. And so 1.63 times 10 to the negative 8 Newton. This is this one here, problem number D. Let's see if we are right. Yes, we are right. We did it correctly. Now you just need to watch that video over. Now, as we are running out of time, the next problem, problem number 13, just 12, 13, is very similar to number 12, and I will leave it up. Leave it to you guys for practice, as I am running out of time in this session, because I still want to do the last two. Okay, going on. Problem number 14, number 13 is similar to that one, and let me just give you the answer for number 13. It is very similar to the one that we just did, and its answer should be 2.33. Should be 2.33. It's this one. It's the correct answer, and yes, you should get 2.33. It's exactly the same, but in this case we just want forces on that particular particle. Okay, so problem number 14. Question 14. What is the gravitational force on a 20 kilogram satellite circling the Earth 6.5 times 10 to the 6 meters? The radius of the Earth is 6.4 times 10 to the 6 meters, and the mass of the Earth is 6 times 10 to the 24 kilograms for a period of 5 hours. Okay, so what's the gravitational force on a 20 kilogram satellite circling the Earth for a period of 5 hours. So what is the gravitational force on that? So first we need, using Kepler's law, we need to determine the radius of the orbit. Okay, so first we need to determine the radius of the orbit. Okay, so the distance between the satellite and the Earth. Using Kepler's law, we first need to determine the radius of the orbit. Okay, using Kepler's third law, we need to determine the radius of the orbit. Let me just check. Still no questions, no one. Using Kepler's third law, we need to check the radius of the object. Using Kepler's law, or third law, we determine, using Kepler's law, we determine the radius of the orbit. Okay, so the radius of the orbit in Kepler's third law would be equal to the cube root, we just rearranged for the radius, mass times the gravitational constant times the period squared over 4 pi squared. If we plug in everything that we know to get the radius of the orbit, the mass of the Earth is 6 times 10 to the 24. G is 6.67 times 10 to the negative 11. The period is 5 hours times 60 minutes per hour times 60 seconds per minute. And that period should be squared over 4 pi squared, giving us the radius of this orbit is 148,64630.54 meters. That is the radius of this orbit. Now the gravitational force between the two, because now we have both of their masses, the mass of the Earth and the 20 kilogram satellite, so we can easily calculate the force of gravity between them. It's the mass of 1 multiplied by the mass of 2, the radius between them squared. Okay, so that it'll be 6.67 times 10 to the negative 11 times the mass of the Earth, which is 6 times 10 to the 24 times 20 kilogram satellite's mass. The radius between them is 1.486463.54 meters, and you square that and you get an answer of 36.22 Newton. Okay, not a lot of force between them, so it's 36.22 Newton. Okay, so the trick there was just to use Kepler's law to determine the distance between the two of them, so it's 36 newtons. You can check. The answer indeed is 36 newtons. Okay, number 15. Okay, the kinetic energy of a 200 kilogram satellite as it follows a circular orbit of radius 8 times 10 to the 6 meters around the Earth. We need to calculate kinetic energy. Now, number 15, the formula that I did not give for kinetic energy is equal to the gravitational constant times the mass of the Earth times the mass of the object divided by 2 times the radius. Okay, so that is 6.67 times 10 to the negative 11 multiplied by the mass of the Earth, which is big M, which in this case is 6.67 times 10 to the 24, or just 6 times 10 to the 24 will give you the same answer, times 200 divided by 2 times the distance of their orbit, in this case r, it is equal to 8 times 10 to the 6. If you work it out, you get that the answer is 5 times 10 to the 9 joules. Okay, 5 times 10 to the 9 joules. First one. Check if we're right. Yes, we are correct, and we are just in time. Okay, so I'm going to say we are done now for this week's session, and thank you whenever you're watching this for listening to me, and I hope you understand what it is that you are doing. And remember, you need to just do problem number 13 on your own, because we do not have time, and it is exactly the same as problem number 12. Okay, now I'm going to say enjoy your weekend, stay warm, and all the best. I know the PHYB students are writing a test, so good luck studying.